Hello everyone, a very warm welcome to this video. In this video, we are going to talk about what are the most common use cases of Mapreduce. Use cases like how do you go about sorting, how do you go about searching, how to create an inverted index, and so on and so forth. So let's get started.
Mapreduce algorithms are the most common use cases. So let's quickly reiterate what we've seen so far and set the stage for this particular chapter. So let's quickly look at so we started with what is Mapreduce. After that, we got to, after learning the basics of it, we got to more advanced stuff. And after advanced stuff, we went to the level 2 where we understood and we then saw how to do joins. It's time to now really put everything together and look at and this video is all about that. So let's understand what we are going to look at when it comes to the most common algorithms or use cases of Mapreduce. We'll talk about how to perform sorting, searching, we'll look at inverted index, tfidf, secondary sorting. These are the most common use cases or algorithms used in Mapreduce, and now we are going to look at them. So let's first start with sorting. So what exactly is sorting? In the most simplistic terms, it's basically arranging things in a certain order. If we wish to sort a certain set of strings in an ascending order in Mapreduce, we don't really have to do anything because the framework takes care of that. So let's quickly understand how the framework works and how sorting could be provided or sorting is available out of the box. So let's say we have 5 strings. and we want to sort that. In Mapreduce, let's say this was given to, so this was, let's say, a big file and there were two mappers. These three strings go to mapper 1. And these two strings go to mapper 2. What we finally want is, with some magic, our final output should look like that should be our final output through some magic. Now, after the mapper, what we get is the same values, and it's during shuffle and sort everything comes to the reducer automatically sorted. And here we will have a do nothing reducer, because shuffle and sort phase automatically ensures that everything is sorted in ascending order, so we don't have to do anything whatsoever. So if we wanted to write an algorithm for sorting, it would look like so you emit key value, and in the reduce shuffle and sort automatically sorts everything based on the basis of the key, so you don't have to do anything. And in the reduce, it's just a do nothing reducer, and your output is completely sorted. This is how you perform sorting in Mapreduce. This is how you perform sorting in Mapreduce. Sorting is extremely easy. Sorting is extremely easy when we are talking of a single reducer. So sorting is extremely easy when we are talking of a single reducer, but becomes very, very difficult when we are talking of multiple reducers. So let's see how things will look like, or how it will be a problem with multiple reducers, and let's see what is the solution to that. So let's say like this, we have data which is big enough, and there are 4 mappers. Or say 3 mappers. And there are supposed to be 2 reducers. So if it was a single reducer, the problem was not there, but right now we have 2 reducers, and by default we have something called as hash code partitioner. So let's look at this with certain data. Let's take the same data. Now let's say John and Jack went to the first mapper. Adam and Bishil went to the second, and Charles went to the third mapper. When it comes out, the hash code partitioner will, based on the hash code, define where each record should go. So let's say after hash code, it's decided that John and Charles, they go to reducer 1, and Adam, Bishil and Jack so this is input to reducer 1 and this is input to reducer 2. Now while these both are individually sorted, when they are processed, what we end up getting and this is not sorted. So this is not because partitioner worked on hash code partitioning and decided to send Charles and John to reducer 1, which is sorted in sorted order, Adam, Bishil and Jack to reducer 2, which is again sorted. But when the final output comes, we'll have 2 files. In the first one we'll have Charles and John, in the second one we'll have Adam, Bishil and Jack, which is not sorted. And that means and that is where we will have to customize the partitioner, and we have a ready-made partitioner called as total order partitioner. So hashcode partitioner is not going to work. It's total order partitioner that's going to do the trick for us. It's total order partitioner that will do the trick for us. Let's understand the basic logic of total order partitioner. Total order partitioner works on the basic premise that if key1 is greater than key2, then for sure partition of k1 or key1 would always be greater than partition of key2. That's a simple formula that it works on. So with that formula, what we could have got is we could have got something like this, because the total order partitioner works with the formula that if key1 is greater than key2, partition of key1 will be greater than key2 or k2. So in that regard, Adam, Bishel, Charles typically would go to one reducer in sorted order, and Jack and John will go to another reducer in sorted order. And the outcome would be it's completely sorted in spite of multiple reducers. So that is how sorting could be performed in Mapreduce. That is how you perform sorting in Mapreduce framework. So let's summarize. So that is how you go about performing sorting in Mapreduce. Sorting in Mapreduce. So a quick reiteration. Sorting is a natural process in Mapreduce. Data, when it travels from map face to reducer phase, it's already sorted in order of ascending order of the key. So technically for sorting, we'll have to have a do nothing reducer. If we have multiple reducers, sorting will not work naturally. For sorting to work with multiple reducers, we need something called as total order partitioner. Total order partitioner works with the following basic formula that if K1 or key 1 is greater than key 2, then partitioner of key 1 will always be greater than key 2. And we've seen how that works. Total order partitioner ensures that with multiple reducers, also we can have a perfectly sorted data. So this was all about sorting. Now let's talk about how do you perform searching in Mapreduce. So searching So both of these are searching. Either ways, things would work fine. So the idea is that given a certain string, we are supposed to find if that string exists in a particular sentence and emit the sentence or emit the document name based on the use case that is given to us. Now in this searching use case, we would typically not require a reducer. Because we are not consolidating something. Yes, along with the search, if the use case was to find the count of the search results, then reducer would be required. So let's add that scenario also. So this is act of searching. Let's see how we would design each and every way of doing things. So first, we will be reading one record by record, and we will find if something exists or the string exists in that particular sentence. So read the variable as argument or through distributed cache. That variable is nothing but search string. And in this scenario, we may choose not to have a reducer at all. Now what we really are looking at is if a sentence contains the search string, let's find that for us. So this is how you will do search. This is how you will perform search. Here what we find is if a search string is present in a particular sentence or not. Let's look at another scenario. Find a string in a document and let's say emit the document name. So here we'll read the search string, and here our each record would be entire. So here our key will be file name and value will be entire document. Now the question would be, how do we ensure that we can have our own input format we are reading, where we are reading an entire file or the contents of the entire file? So if the document contains search string, we can have document name emitted. So by the end of it, we'll come to know which documents contain this particular string. So this is another case where you would want to search. So in the first case, let's say your output expects or is expected to have a sentence. In this case, your output is expected to have a document name. In both the cases, we don't need count. So we don't need to aggregate all the search results. And because we don't need to aggregate the search results, it's perfect that we don't have a reducer at all. It's okay. We'll be able to manage. Now let's look at the third one where we are supposed to have the sentence also and the total number of count also. Here what we are supposed to have is find a string in a sentence and emit the number of sentences that have the search results also. So here we'll simply read each and every record or sentence. If sentence contains search string, we will emit search string in sentence. Now the input to the reducer will look like and in the reduce So if we are supposed to aggregate the number of the count of the sentences that had this particular search string, in that case we will need a reducer where we consolidate the number of sentences that contained that particular search string. So here we get the number of sentences that have this particular search string. So that is how you will go about performing search. So that is how we go about performing search. That is how we go about performing search. So what we've seen so far is how do you go about performing sorting and how do you go about performing search. The third algorithm that we are going to see is called as inverted index. Let's understand what exactly is inverted index and how could we achieve this in Mapreduce. How could we achieve this in Mapreduce? So let's understand what is inverted index. So the section at the end of the book can also be referred as inverted index. Let's understand. At the end of the book, what you would have is, for example, it's an RDBMS book. We'll have term normalization. So what we have is the term and the occurrence. In real world also, a lot of search engines, in fact, most search engines follow the same principle. What they create, the search engines, what they create is inverted index. That is, you have set of documents or web pages, and what we do is we have a keyword or a search term and which web pages on which web pages a particular keyword is existing. And that is how search engines, they create something called as inverted index. That is how search engines create something called as inverted index. So let's understand how we would do that in Mapreduce. How we would do that in Mapreduce. So we have, let's say, a couple of documents. So let's say we have 4 documents and each document has, let's say, a sentence. What we finally want as output is So this is kind of an inverted index. Now let's look at how do we achieve this in Mapreduce. So the first thing is, once we read the line, we'll extract the name of the document. That is possible when you have a block. When you have a block, you can extract which file this block belongs to. So let's say in this case, with the help of block, we'll come to know that this is document 1. And for each word, what we are going to emit is so like this. For each and every word in set of documents, we'll come to know that this word is available in which document. And of the mapper, what we get for a certain word is something like and let's say R was present in a certain document 10 times. In reducer, so what we end up getting is R is present in. So R is present in document 1, 2, 3 and 4. It's present in all the 4 documents. And that is how a lot of search engines they work. So you have a keyword and you know which page, which web pages is this particular keyword available, is this particular keyword available. That is how we go about performing inverted index or creating inverted index. So this is how inverted index works. So inverted index is an act of creating an index where we have a keyword and list of documents in which keyword is present. Extremely popular in the field of search engines. At the very base, the search engines use this algorithm to figure out which web pages a particular keyword is available. From the mapper side, or in the mapper, we will emit a keyword and the document name. The document name can be extracted from the block name. And once mapper is done, during shuffle and sort, what we end up getting is a keyword and list of all the documents that have that particular keyword. And in the reducer, what we'll do is we'll remove the duplicates and display keyword and list of documents where that particular keyword is present. So that is how you go about creating inverted index. So a quick recap, what we've seen is what is sorting, we've seen what is searching, and we've seen what is inverted index. Sorting is an act of sorting. We can do it with a single reducer and multiple reducers. Searching is an act of finding certain information. And the third is inverted index. And inverted index is an act of creating an index. It's creating an index where we have the keyword and the list of documents that contain that particular keyword. In the next video, the part 2 of this video, we look at the remaining three algorithms, that is tfidf, word co-occurrence, and sorting. In this video, we are going to talk about the remaining three algorithms of Mapreduce, that is tfidf, word co-occurrence, and secondary sorting. So let's start with tfidf. But before that, let's quickly recap what we've done in the previous videos. So we've already seen that what exactly is Mapreduce and the components of Mapreduce. In the previous video, we saw how do you go about performing sorting in Mapreduce, and how sorting is a natural process when there is a single reducer, and for multiple reducers we'll have to use total order partitioner. We saw how to go about searching, and after that we understood how exactly we should go about creating inverted index. The next algorithm that we are going to talk about is tfidf. Let's understand. tfidf stands for term frequency inverse document frequency. It stands for term frequency inverse document frequency. It helps us understand how important is a certain word in a document. Let's understand the logic behind it. Merely counting the number of words or number of times a word occurs in a document is not a good measure of its importance. Let's take a simple example. In document 1, the is 54 times. From the face value, looks like the is the most important word in this document because it is out there 54 times in a document. So word the is 54 times, and from the face value, it's the most important word in this document. But hold on. In every document, the is present multiple times. So then in the entire pile of document, the is present everywhere. So probably the is less important, or maybe it's a stop word. So merely looking at the number of times a word occurs in a single document is not a good measure of importance of that particular word. You'll also have to look at the occurrences in other documents, and if the word is way too common, then probably it's a stop word. The, if, this, of, these are the words which will be there multiple times in each document, and probably that makes them less important and something that we should not be worried about. And tfidf exactly helps us find that. Let's look at one more scenario of a situation like this, and we will then see what exactly is tfidf. So let's say we have user 1 and it's a music recommendation system. So has So we have 5 users, user 1, 2, 3, 4, 5. And user 5 is just new to the system. So we are supposed to recommend music to user 5. Now, so based on the location, based on other preferences, looks like user 1 and 2 are, or user 5 is most similar to user 1 and 2. So what we are supposed to do right now is, this is the data set we have, and we are supposed to recommend music to user 5. Now if we have to recommend music to user 5, our goal is to recommend something that's extremely personalized, not something popular, but most personalized to user 5. And based on the data we have, user 5 is most similar to user 1 and 2. So what is that we will recommend to user 5? Let's look at it. Looks like user 1 and 2 both have Beatles. So let's recommend Beatles. But hold on. Our real goal is basically to give a very personalized recommendation. But Beatles is not personalized because Beatles is everywhere. So probably it's less important. So the recommendation that would be made would be first 3 and then later on everything else. So the point is, it's called as term frequency inverse document frequency. Let's see how it works. So let's say we have these 4 documents, and let's say we want to rank, and let's say find out So the question that we are supposed to answer is, who is more important? Which word is more important in document 1? Is it who or is it where? Is it who or is it where? So let's understand this. The way tfidf works is, first it finds out the number of occurrences in a document. So in document 1, who is one time and where is one time. Who is one time and where is one time. So that is nothing but this is called as TF, term frequency. Now IDF is calculated by log of n by n. So let's understand, log will inverse out things. N is total number of documents and n is number of documents with the word so that means for who it will be log of 4 by 4. There are 4 documents and in all 4 who is there. And for where it will be log of 4 by 2. Log of 4 by 2. So now let's look at what is log 4 by 4 and log 4 by 2. Log of 4 by 4 is 0. Is 0.30. So log of 4 by 4 is 0 and this is 0.3. So importance score of who is 1 multiplied by log of 4 by 4, that is 1 multiplied by 0, that is 0. And importance score of where, because where is present only in 2 documents, document 1 and document 2. So where is more important than who? Where is more important than who? This is how you derive which word is more important. This is how you derive which word is more important. So tfidf is nothing but term frequency multiply by IDF. That's nothing but this is how tfidf is calculated, and this is how tfidf works. Very popular for recommendation engines or finding importance of a certain word in a document. Imagine if this was the logs of customer feedback, and you have so many documents which have feedback of a customer. In a certain document, what is the importance of a particular word from millions of documents? tfidf could dig that for us and let us know how exactly it works. Now let's talk about how do you really achieve this in Mapreduce. How do you really achieve this in Mapreduce? So this is what we are trying to achieve. Actually, what we would need is 3 Mapreduce programs. In job 1, we will compute TF, that is term frequency. In job 2, we will compute the capital or the small n, that is number of documents in which the word occurs. And in job 3, we compute tfidf, that is these are the 3 Mapreduce programs that we will require. So now let's understand what we will do in each and every Mapreduce program. What will be the what is that we'll emit in each Mapreduce program, and then we'll summarize. So job 1 is supposed to give us TF, that is term frequency, that is basically word count. It's nothing but word count. So let's see how we will calculate word count. In our map, we'll have document name as input and document contents as output. For each word, for each and every word, we will calculate word count in that particular document. And what we will emit is the term, the document name. Now document name is not directly required here, but we will require that ahead in other jobs, so that's why we'll put it, and 1. So this will keep on telling that yes, it's creating a pair and saying that yeah, it's once, twice and all. And in the reducer, we'll aggregate the word count, and what we will get is tf, that is nothing but word count. So job number 1 is exactly same as word count. All we are doing is the number of times a word occurs in this particular document. So in our example, the possible outputs here would be who hash document 1 and where hash document 1. So what we get is who was once and where was once. That's the intention of job 1. It does word count for us as per our previous example where who was also one time and where was also one time. The next job, we will focus on calculating the number of documents that the word occurs. So let's look at we are trying to calculate small n. So our map input is term hash document name comma word count, and our output will be term document name hash term frequency hash 1. Here we are trying to just calculate the number of documents in which the word is occurring, and that's our mapper output. In the reducer, we will aggregate the number of documents that had that particular word. So here we are just calculating one, that is which document had this word or not. We were only interested in that. So here we aggregate and our output looks like so here we have term frequency and we have small n. So by the end of this particular job, what we will see is we will see who is document 1, term frequency of who was 1, and it is present in all the 4 documents. And where was present in 2 documents. So here we get small n. So that's job 2. By the end of job 2, we've already got n, that is small n. And in job 3, we will simply, now that we have small n and tf, we will simply perform tfidf in the mapper itself, and we'll say tf multiply by where n is total number of documents, and in reducer we'll have do nothing reducer. Of course, this is our map. This is our map, and n is total number of documents. So what we've seen is we will require 3 jobs. In first we calculate tf, which is word count. In second we calculate n small n, and then third we just multiply the whole thing. So tf idf can be achieved in 3 Mapreduce jobs. And this will give us the measure as to which word is more important, and it can basically create those rankings for us. This is how tfidf works in real world. So let's understand tfidf. So this is how tfidf works. It works on the principle that if the word is present a lot of times in a document, but it is present everywhere else also, then probably it's more common and less important. That is tfidf, term frequency inverse document frequency. Term frequency inverse document frequency. The next algorithm that we are going to talk about is extremely simple. It's called as word co-occurrence. So what exactly is word co-occurrence? So given a set of documents, which word occurs most frequently near another word? So for example, take an example. So this is how you calculate, or this is what the algorithm is all about. It's trying to find with this word which is the most frequent word that's used, with this word which is the most frequent word that is used. That is called as word co-occurrence. Very heavily used to find relationships, like people who were talking of, let's say, skydiving were also interested in bungee jumping, and if you happen to be interested in skydiving, you may get a recommendation that, hey, this guy is also interested in activities that are near or similar to this, and that's how you find people with similar interest. A lot of social networks do that. Dating sites would do that. Product recommendations, whenever people are talking of a product A, they are also referring product B, so probably they are related to each other. So word co-occurrence tries to find that for us. Word co-occurrence tries to find that for us. How it works, let's understand. We'll take for each word A near word B. Now this criteria A pair B, or we can have our own custom writable and a pair of A comma B 1. So we continue getting the counts. Now input to reducer would look like reduce and what we get is A comma B were near each other 50 times, so probably they are related. That is how we get word co-occurrence. That is how we get word co-occurrence. That is how we go about calculating word co-occurrence. That is how we go about calculating word co-occurrence. So, quick recap. When it comes to Mapreduce algorithms, we've so far seen 5 of them, 5 most important or 5 most frequent use cases. We've seen sorting, which is natural in Mapreduce, with one reducer. With multiple reducers, total order partitioner would be used. Searching is basically finding out a certain word in a pile of document. Inverted index is basically used for ranking for search engines, where you have keyword in the list of web pages where that keyword is present. tfidf is term frequency inverse document frequency, where we are trying to find the importance of a certain word in a pile of documents or in a single document. To do that, we first see the count in a particular document, and then we see in how many other documents the word occurs. If the word is very common, then probably it's less important, and tfidf does excellent job at finding that for us. The next one is word co-occurrence, where we are trying to find out if a certain word is there, what is the most frequent word that occurs with that particular or this particular word. That is what we are trying to find in word co-occurrence. So we create a pair. Say for example, with Apple, Samsung is used the most frequently, and we say that yes, these two words are somewhere related. This is how word co-occurrence works. The next algorithm that we are going to talk about is secondary sort. So let's understand what exactly is secondary sort. So let's take you have secondary sorting. So before the data reaches the reducer phase, the data is sorted based on the key. And we've already seen that. So just to reiterate, So if this was the document, or this was the contents of the document, and if they were to pass through a mapper, before they get to reducer, this would invariably be sorted. So it'll be Ashley, Bill, Charlie, Jack and John. So if this was the key, it would invariably be sorted for us. It would be invariably be sorted for us. And that's how it works. And we don't have to do anything additional. It's kind of part of the core framework. It's part of the core framework. But what if we have a situation? The situation is so this is what we have from our mapper. This is what we have. This should be going inside the mapper. Let's say in this case, our key is first name. Our key is first name. Okay. So what happens before it gets to reducer is this is completely sorted, and then it goes to the reducer. Sort worked perfectly for first name, but if we carefully look at it, Bill and Jack could have been better sorted, What we would have liked to have probably is what we should have probably had is something like this. We should have probably had something like this. To do that, what we'll have to do is we'll have a composite of so what we'll have is a composite of first name and last name, and based on that we'll sort. So this act of sorting based on a composite key is called as secondary sorting. This act is called as secondary sorting. So let's quickly understand how we will do that. Our mapper will emit let's say city. In partitioner we will partition based on primary key only. So for partitioning we will only be using primary key. There is absolutely no need to use secondary key, because with partitioning what we are trying to achieve is the same keys should go to the same reducer. So when it comes to partitioning, we will keep it extremely simple and have something like first name. Let's put it this way. So our partitioner will be absolutely on the primary key. There is absolutely no need to have anything else. And after we partition, we will have two comparators. These two comparators will basically, comparator is to compare. We'll have two comparators, sort comparator and group comparator. Sort comparator will sort if names are same, and group comparator is to figure out if primary keys are same or not same. So group will basically group them and sort will basically sort. So in our case, John McCain should be after John Ashley is taken care by the sort phase or the sort comparator. And that is how we achieve secondary sort. So the end of it, what we will end up getting is data that is sorted in this particular with its first name and last name. So that brings us to the end of this video, where we've seen all the use cases or the most important use cases of Mapreduce. So we saw 6 most important use cases or algorithms. We saw sorting, searching, tfidf, we saw word co-occurrence, and we saw secondary sorting.